Good morning, everyone. So I'm very happy today to attend the CNCF conference today, and today we're going to talk about Thanos today. And I want to thank the previous speakers for the introduction, the kind of like a background for us. And today we are going to talk about how we use Thanos to achieve high availability and scalability. So, self-introduction. So my name is Guo'an, and I joined Alibaba in 2016, and I work in container for about container in the host, and now I work for Kubernetes and SRE. And my colleague joined our team in 2018 and mainly responsible for the data deployment ecological system, and he's mainly responsible for that part. And today we're going to go through 4 parts. Firstly, we're going to make a brief background introduction, why we do this, what is the meaning, and the second, we're going to talk about the construction process, and the third, how we use decentralization data and how it evolves, and the fourth, and the visions that we have for the future. And for the first, I will be responsible for the first 2 parts, and my colleague Li Tao will go through the last 2 parts. And firstly, what is the background? So, before we start, I want to do some scenario analysis. How can we use that data? And this is the policy engine, and this is what Alibaba wants to, the project that we are going to have in Cruster. And what is the meaning of it? So it's that when there's conflicts, we can adjust the QS to ensure the stability of our resources and our business. And the second is the center scheduler. So for instance, there are a lot of scenarios we need online and offline deployment at the same time, and all those offline deployment can be used, and how can we better execute those data? And also we have an algorithm team to analyze whether the algorithm that we use is reasonable. And also, next we have a resource operation, and it can see that for the business growth and the business change that we can actually plan the server. And because every year Alibaba will buy a lot of server, and our resource operation can make sure that what kind of server that we need to buy to meet the needs of our future servers. And also dashboard is mainly responsible for our data management, and this is kind of like a use case scenario analysis for us. And next, what is our plan and what is the capability that we are trying to have? First, so we want to have this kind of instrumentation. We need to have this capability to identify problems, and we need to analyze and solve the problems. And also on the left, you could see that we have a lot of data on the time series, and including hardware metrics, OS metrics, application metrics, and they are all stored in the time series server. And on that basis, you could see that the time series implementation, and we can monitor the dashboard, and we can have these kind of like data coverage, and we can build a lot of capabilities, and this kind of like expansion of automation, and we can have monitoring and error alerting, and use this data to optimize our container and achieve higher sales and the turnover rate. So how can we use those data to solve our problems? You may see that you may know that all those problems are large scale. So we have those problems on some version of kernel and the time series database have this kind of aggregate capability, and it can be stored in the database. It not only include metrics but also include event. So all those Kubernetes system metrics are also installed in there. So it's kind of like an offline database. So on that basis, we will have these other capabilities. Our algorithm engineer and will do their work, and our data analysis team will also do their work on those bases. And our DevOps engineer can do some operations on the analysis that we have. So this deployment system and all those key capabilities that we want to have. So those are the analysis that we have. And next, the so on the capabilities that we have and what is the architecture that we are going to have. Actually, we have these two parts. The first part is the customer end. So for the customer end, it consists of two. So it's called Wally. So you might actually see the. I've actually watched the movie.
机器人总动员里面那个瓦里，对吧？他就
So
是
Wally
负责收集各种各样的脏的东西，然后
in
把它
robot
收集到自己这儿。
in Wally E. So actually in Wally, this movie, it's just that's how we get the name, and we get these kind of like storage, and we have persistent data, and all this data will be put in the observability database, and we use this paper data that matrix, and we do it. And this we need to ensure a long life cycle to have a long serving lifetime. And if we have a problem, so we need to make sure that data stays there. So with container storage, we have a lot of those containers, and the Kubernetes fails, we cannot see that those Kubernetes fail. So we need to make sure the data is can be successfully retrieved. And we have this adapter and inference store and the matrix server and the VPA. They are actually connected, all those 7 systems. So that was the first part. We introduced the background, and the second, we are going to talk about the not agent. So how we actually achieve the functions of Wally. So the design principles. So we actually have several design principles, and the first is availability. We need to ensure high availability, and it will not fail easily. So there are 3 small little principles. So we need to have independent metrics, and also we need to have this kind of low dependency, and you will not have any effect on that. And if there's no accident, we will never restart the system. And the second is high performance. That's also an important principle that we have. And if we have like a policy engine that needs to use our data, we have this QoS adjustment, and we need to have this high performance local query capability and future prediction capability, and have this kind of like real-time query and this kind of like future prediction. And the third principle is low cost. Because for everyone work for agent, if we run an agent, it costs a lot of resources. It's just not reasonable. So we need to control the cost. So there are also 2 small sub-principles. So we need to use less CPU, and we need to make sure that we only pull one metric for one time. And maybe there are a lot of duplicates, but maybe like a lot of people are doing it and I'm doing it. So, but for us in Alibaba, we only do it for one time.
you need to be flexible enough. So today, if you want to get in or delete or update one data source, you can just do it independently. So we have three principles. First is that for every data source, they have their own collection cycle. For example, if you want to collect the CPU, and you do it frequently, for example, for 1 time at 10 seconds or 15 seconds.
因为我们现在磁盘都非常大
But
嘛，
for
对吧？
database,
那可
since
能我
we
一个
have
小时或者
large
半个小时我采
volume
集一
of
次就好。这
disk,
样的话也能
we
尽量
can
的
do
减少我们
it
的系统开销。
maybe
第
half
二个
an
的话就
hour.
是说，我们要支持聚合能力。为什么支持聚合能力呢？就是
This
说，
kind of
今天
capability.
在宿主机上面，
So
很
in
多的数据源是
our
它都是
host
counter 类型的，
machine,
比如说像CPU 的那个
for
使用
example,
时
the
间啊等等，这
CPU
些东西都
use
是一
time,
个 counter 类
this
型
kind
的。
of
我
a
们在展示的
counter.
时候，实际上
So when we are
在
showing
展示之前一
this,
定要对它进行聚合
both
计算
showing
的，
them,
把它
we
变成
need to
频
have
率
a
啊等等。所以说
kind
本
of
机一定是要提
aggregated
供一些聚合能力，这
accumulation
样的话尽可能的减少
computation of it.
后续我们
So
做
to
聚合的时候的
reduce
开销。
the kind of
第三个的话，
overhead
就
that
是
we
说
may
我们
have
希
later
望所
on.
有这些插件
And
化的
third,
组
we
件
hope
都是
that
可以
all
独
of
立发布
these
的，对
components
其他
can
组件没
be
有任何影响。
released or
以
delivered
上是我们
independently
想到
without
的
the
我们在
influence
安
on
全链路上面的一些设计的
other
原则，
components.
大概这4
These
点。
are the design principles that we have thought.
然后下面的话就是给大家介绍一下我们
Next,
这个
we
单
would
机链
like
路的
to
这个整个的架构
introduce
是什么样的。
the overall
我们这个主
architecture.
要是大概分了2部分。
So these
一部分是
are
分
mainly divided into
process
two
它主要就
types.
是说
First is the
负
main
责从我们底
process
下不同的数据源
demo.
去采集数据。
They just collect the data from different data sources, and they are 4 components under it. First, the aggregator, which is mainly responsible for aggregates many of the data into a new one. For example, the encounter to aggregate into a gauge one. Or for example, you have many containers, you want to do an average of them, we can do them in this. And exporter API is mainly used for our centralized storage. So for example, Prometheus, so our central storage can get the data easily, and the query API can just check the data change in the past or predict the change of the data in the future, and the Spectre is mainly used to collect different kinds of data through our various plugins. And for the second, in our plugins, we have supported many kinds of plugins like node, kernel, container storage, and later on we will have like the network. We have many plugins, and I would like to use node plugins as an example. We have achieved several interval, and the name interval and clamp. According to my previous introductions, you can predict that actually these are the intervals that Scripper might use. So every time Scripper wants to collect, they will just according to this interval to define how long to collect next time. And root is cooperated with aggregator, and they can just get all the rules that we are using today. And according to some of the database to do the aggregation export. For example, today I've already have too much data according whether it is the original or the one that we got later on, and they can be defined in export. For example, I have got 20 of the CPU and only 2 to 3 of them can be used today. So these are the 2 parts. One is our main process, and second is the plugins, how to use. So when the main process needs to visit the plugins, and the plugins can be started, and once they have finished visiting, and these plugins will just be closed. You can imagine that every time they will be launched and to be used in the circuit. And once I have operated this function and this plugin can be closed, this can also reduce our system overhead in the maximum extent. And all the container function, once you have upgraded and next time you use it, they can be upgraded automatically. And these are the introduction. And next, I would like to introduce the practice ways. And first of all, we have chosen the Prometheus TSDB engines and used the storage of Prometheus we have, put them into our single machine to do some small changes so that to guarantee the current data that we're going to use or stored. So actual TSDB engine has a quite excellent performance, and also they have many of the simple function embedded in it, and they have realized the TSD this kind of construction and compress. And later on, for our plugins, we have chosen Go plugins, and you can just search it online. Also, we have achieved the standardization of all the interface of the plugins, and this later on we have also achieved a combined HTTP API. That is the Prometheus query ability because they need to be used for the local query, and also when our centralized storage, when they are grasping data, we can provide them the data that they need, and also we have achieved event store functionality. We know that some of the formats of the data cannot be stored, and we need to store them in another way. For example, like these events, like GSB, and whether what kind of formats they are, they can just store locally. These are some of the implementations that we are using now. And lastly, I'd like to appreciate our open source committee and also all our engineers contribute to this open source community. So since we can achieve this kind of fast developing and aggregation because we have already sending a very high standing point, we have leveraged the advantage. We have used Golang and we have used Go plugin to achieve the reformation, renovation, and also we have used PrimQL and some of the technologies there. So in these slides, I would like to briefly introduce that many of us here today, you shouldn't have data locally. So what is the meaning of it? And this graph can briefly introduce that actually for our quality engine, how to adjust the QS to guarantee the stability of the business. We can see that actually for this, the response time of this business is normal, but once this resource sharing is appearing and it has some changes. So actually, we can use the technology to discover some of the irregular things, and this kind of some changes and differences in it to guarantee its normal function, to guarantee the stability of the business. So these are some of the process that we have gained. If you have the interest in the policy engine, and you can see the craze this of the open source speaks. And next, I would like to invite my partner Li Tao to introduce our how can we use Prometheus and Thanos in our centralized storage. Well, hello everyone, and I would like to introduce in Alibaba and some of our experience in using Prometheus and Thanos. First of all, I would like to introduce Prometheus because initially they are a kind of system monitoring and alarming package, and in 2016 they have joined CNCF, which is an independent open source program, and also many of the companies and the organizations, they have joined the Prometheus and they have very active developers and users community. Also through Kubernetes and the console or documents, they can just identify our object, and based on the ATP through pool to get the object data. And also Prometheus support the alarm system and can send the alarm data to an independent management tool. And also Prometheus is supporting a very flexible checking language and can be used for many dashboards. And as for our Prometheus, this kind of multi-dimension language, but not only for the monitor of the machine, but also for the microservice architecture. And next, so from the kind of a scalability plan of Prometheus, I would like to illustrate on this. While we are deploying the Prometheus, the commonly used ways, we will just consider from different clusters and schedule the different resource for them. And this is suitable for the scenario that we have thousands of machines. And for this kind of working mode, they don't need to go to the public network and can reduce the unnecessary overhead in the network. Also, this kind of deployment method can satisfy the demand of many SMEs, but in the scenario of Alibaba, we have several dozens of the clusters and we have over 100,000 of the pods, so we cannot maintain it through this way. And also, a very big problem of it is that if we want to check a service of its current function in all the machines, we cannot do it. We don't have a general view. And another way of scalability is that maybe your cluster is not big enough, but still you're facing the kind of a loading pressure of a Prometheus. So we can build a Prometheus for every application. So if your application is also enlarging, then this method is not suitable at all, because for Alibaba we have over tens of thousands of applications, so this method cannot be used in this scenario. Also for Prometheus, in order to solve this kind of general view problem, they have used a federation, and they can just input the data from another architecture and to have a hierarchy monitoring system. So if we want to see the request of every per second in every machines, and we can just collect the data, all of the data in this machine, in this room, and also in the core machine room, we can just deploy Prometheus and to get the data after the aggregation. So Thanos can check the relevant data from the general Prometheus and to get the sum and to know the request per second of this service. But the problem is that, first of all, you need to manage the aggregation rule. When you have too many aggregation rules, it's a problem for you to maintain and manage them. And also for the federation, they are more useful for getting the data after the aggregation.
And also, see a colleague of mine, they actually store all the data, so I think that's probably problematic. So you can see that it also has something to do with the performance and scalability issue. And because the data storage is just huge, and when you pull the data out, and they will face a problem, there will be a bottleneck of calculating the data. And so you will have a lot of monitoring, so you cannot support all the service that you need to provide. And additionally, so this kind of federation, it also has a lot of problems So if you pull the whole data out, and there will have the data query, and it will pull all the data out, and it's kind of like queuing of the texts, and the cost will be high, and there will be some reliability issue. So when we were doing this, so we were talking about we need to lower the dependence on the outside. And if we introduce another Prometheus, then there's another point that might have a failure. So if we transfer data on the public website, the risks is even higher. So when you use Federation, you need to consider how can you use this kind of like data monitoring mechanism on the higher data, and instead of using higher Prometheus, and also this kind of for the federation to work, there will be a problem. So the data you pull might be lagging behind, and you might lose your data. For instance, if you use public network, and when it runs out of time, the data might be lost. And if it's just a demo, you can tolerate this kind of error. But if you pull out all the data, the error will be magnified, and this is not acceptable. Another thing that we could use to scale Prometheus is actually have this kind of like federation and use this kind of like scalability. And this plan also has a problem, because for each Prometheus, when you have this kind of like algorithm to pull the node of metrics, and on each case scenario you have this kind of like different aggregating rules, and on the central Prometheus we put the data out, and then the biggest problem is that the maintenance cost is extremely high, and the plan would be super complicated. And so in the mechanical room, we have like tens of thousands of like this kind of similar structures, so the issue would be quite complicated. So if we want to achieve this kind of like high availability, so you can see that in our environment, we cannot accept this kind of like status, because we need a higher availability. So we need to have multiple Prometheus and have this kind of like similar data, and use similar configs to pull similar data out, and use this kind of like federate. So the biggest issue here is that for each case that you run is independent. There will be a latency in each case, and there will be minor differences. And if we use this kind of like global view and have this kind of like data query, there will be some difference. Maybe, for instance, if you refresh the page, it turned out to be different. And we need to align this kind of like Prometheus, so to connect the different Prometheus and send the query to a same Prometheus. But this also brings another problem. So this will waste the resources of other Prometheus, and all the query can only go to one Prometheus, and other Prometheus are only responsible for pulling out data, and the resources are not fully utilized. So Prometheus actually has a lot of tools that can be used for scalability, but it does have a lot of problems, and in the community we do have solutions. So in the end, we decided to use Thanos. Thanos actually have this kind of a compatible API. So they have this long-term metrics retention engine, and they have unlimited data retention and storage. So I will not go into details. I just want to tell you how we use Thanos for our global view and what is our experience. So this is how Thanos work with Prometheus. So this is the most common deployment. So it actually has two parts, sidecar and Querier. So sidecar is deployed with Prometheus, and the Querier can be put in all those different clusters. So they are compatible, and so when you send a query request to the querier, and those will be further sent to the sidecar, which will pull out the data and send it to the central Kubernetes nodes and send it back to the customers. And because of the instability of federation, and these actually effectively solve the problems of availability and can help us to get all the data. And I also want to add that when we use Prometheus, there was one problem that if you have kind of a service needs to work across different segments, and the functions that we had could not work in that case of in that scenario, but Thanos could work, and that's kind of global view deployment that we have. So in our mechanical room, we have this query deployment, and it connects to different query systems and forms this entire system, and all the data will be sent from the main cluster to the subclusters in different mechanical rooms and will be returned to the client. And this actually helped to address Alibaba's issue in most of the cases, and Thanos could help us to support our data storage requirements. Also, some other works that we did, and in the customer target discovery. So you could see that because, for instance, we have not enough data storage or some other issues, so we need Prometheus to stop automatically pulling our data. So for Kubernetes and this kind of discovery system, so actually Thanos could help us to address the issue. It supports Kubernetes, and in Alibaba, because our business and our some other historical issues because of all those elements. So we have this Kubernetes and other discovery system. So we developed this kind of components, the custom-made target discovery. So it can verify all the data. It will work with the same format, same as Prometheus, and Prometheus can then answer our requirements accordingly. And also configuration management. So if it's just one or two Prometheus, you can manage it manually, but we have so many Prometheus. And also we have this kind of change of configurations of Prometheus, and there's no centralization tool for Prometheus, so we actually developed a tool ourselves. So we have this kind of central management tool, and users could actually send this kind of change of configuration, and we use sidecar to put it on the side of the Prometheus, and it will synchronize all the data and put it locally, and Prometheus can load the data when you send a request. So it actually helped us to address the issue. Last part is thinking about the future. So when we use Thanos and Prometheus for it's been a while now, so we've been thinking that what are the enhancements, what are things of they can improve. So we think the most important thing is authentication, because security is top priority, and it is quite important for us to use this kind of authentication process and help us to authenticate who are the users that we have, and to have these authorized requests, and to authorize them to only use part of the data, and have these kind of targeted management methods, and to have a more precise target and flow control. And the second, about query cache, and we actually, when we rewrite these kind of data, we need them to cannot be remodified, and whenever you check it, the data should be the same, and we need to for the time knots and every data, we need to return the data and store it locally so we can go back to the data quickly. And third is query safeguards. I think Thanos and Prometheus both have this kind of function, but we need more precise management. Fourth, we want them to be integrated with Apac Flink, so the calculating capability of us can be enhanced. So we can integrate with Apac Flink and support more calculating capabilities. There's a problem with Prometheus is that it's a single it's a single host, and then when you run it, they will have some bottlenecks in terms of the calculating. So this is all we want to share. Thank you very much. Any question? So actually, I do have a question. Because we are monitoring. So what are the strategies when you monitor the cold and warm and hot data, and what is the differences between online and offline data? So for the first question, so actually, what are the strategies that we use actually for the data that we have? So actually, it has actually run from 10 seconds to minutes and even to hours. They are different, but then we can make sure that for the important data, the particle need to be small and it need to be fine grade monitoring, and the grain need to be finer. So it's just not like one time data or alerting data. If it's like long time away from us, maybe we will have a compactable sample and the retention, maybe we'll delete the data. So actually the strategies are quite complicated. So if you have specific requests, we can talk later in details, because I cannot summarize it in one or two sentences. The second question, I can't remember it. Could you please repeat it? So the second question is, so what is the particle, the grain, and also for the online and offline data, what is the response time? So for the online data, so it's actually real-time data. So we actually pull the data every 10 seconds. The latency is quite low, and when we quite so we have opportunity for another question. So I'll just answer this question for. So when we send the data to question queue, and we don't have this kind of like but we will just have this long-term and Prometheus local retention, so it's within seconds. The latency will not be long, and also the APAC Flink. So we will have more alerting and aggregating rules in the future. One more question. So I noticed that you didn't use object storage by Thanos, so you actually locally store the data by Prometheus. So for every data center, how do you store the data by segments, or how is the deployment, or Kubernetes? Or is it on the Kubernetes or physical or virtual host? So actually, for long-term storage, our cloud, we actually have our own object storage. We have Pangu. Thanos, it has long-term storage, but the interface is not connected. So we have this Pangu interface. ，and in allowing object storage and also for these kind of like data, we want to store it locally, but we do have some problems that when we have replication, we actually for every one of us, we store a lot of storage, and when a packet is broken and we need to copy paste it one on one, and we don't have a lot of like original sources, and we do have this kind of like long term intention. And for also for Kubernetes, whether we run it on Kubernetes or physical host. So actually, on a lot of scenarios, if it's just a small scenario, and if you scale it up, and if it's like tens of thousands, the Prometheus can be managed on Kubernetes, and also the Thanos can be also you used to manage all those data. But in our case, we have so much data, and we cannot run the data on Kubernetes. We have like thousands or tens of thousands of cases. The capability will be too small. And also, second, because the link is actually connected to stability of the whole system, if we have failure, we need to make sure that the link will be not affected. And we don't put Kubernetes of the business side with us. And also we have these kind of independent Kubernetes, and to actually change and to make it adapt to large case scenario, and we're still in revolution, and we still run it on the container. So our time is up. If you have any question, please contact us. Thank you.